Hello, chemists! This is Miss Pluchino, and you're watching lesson 6.6 on limiting reactants. In today's lesson, we're going to talk about what to do when the reactants are not present in equal stoichiometric amounts. So it's going to be a little bit more involved than the previous lesson with ideal stoichiometry, but it's really going to be the same principles applied. In my opinion, this is the most challenging lesson of the unit, not because it's particularly difficult, but because it's just a whole lot of steps and a lot of math to keep track of. So, as I've said for the last couple of lessons, make sure you've got your calculator and reference table ready to go. Goals for today's lesson. We're going to be able to determine which reactant is limiting when given starting quantities of each. We're going to be able to calculate the mass of product formed based on the limiting reactant. We're going to calculate the mass of excess reactant remaining, and we'll be able to calculate the percent yield of a reaction. So a lot of math again, so make sure you've got a calculator, and let's get started. All right, so first I want to start with just some basic terminology. We're going to talk about limiting reactants today, and all a limiting reactant is it's the reactant that is going to run out first in a reaction. It limits the amount of product formed. So it is present in a lower stoichiometric amount than the other reactant. And at this point in time, we'll just look at reactions that have two reactants, nothing more complicated than that. The other reactant will be called the excess reactant. It's the reactant that is present in excess. It's going to be left over at the completion of the reaction. So this happens all the time in chemistry. You go into the lab to run a reaction, and usually you've got one reactant that is going to be present in a lower quantity, and then you're going to load it up with the excess reactant to try to ensure that all of the limiting reactant actually reacts. So this is very, very common in the lab. In order to figure out which is which, because of course they're not labeled limiting and excess, we really just have to determine how much product could be formed from each reactant. So you have to kind of go through the calculation that we did in the previous lesson for both reactants instead of just one. And whichever produces the smaller amount is our limiting reactant. Good. So we'll go back to our bicycle factory, and we'll kind of talk a little bit more about limiting reactants. So we can see we've simplified our tricycle reaction. We've got 3 wheels to 2 pedals, and that's going to make 1 tricycle. We took the seat out of the equation. So based on, look at this number, I'm like 1, 2, and 3. And number 1, I've got 10 wheels, and I've got 4 pedals. Based on this, I can make 2 tricycles. I'm going to run out of pedals first. In other words, pedals are my limiting reactant, and they're going to really dictate how many tricycles I can build. So that means wheels will be my excess reactant. At the end of this reaction, after I've built my 2 tricycles basically, how many wheels are going to be left over? Well, I know each tricycle requires 3 wheels. 3 plus 3 is 6. 10 minus 6 is 4. I should have 4 wheels remaining. Let's look at number 2. I've got 15 wheels and I've got 12 pedals. All right, let's see. So 15 divided by 3, that means I can make 5 tricycles. I got 12. 12 divided by 2 is 6. I can make 6 tricycles. That must mean my wheels are limiting. So I'm going to be limited to making 5 tricycles. My wheels will run out first, therefore pedals are in excess. If I make 5 tricycles, 5 times 2 is 10, 12 minus 10, math I can handle, 2 pedals. Try out this last one on your own. All right, we've got 12 wheels, we've got 12 pedals. Oh, it seems like they're present in equal amounts. Well, be careful. They're not used at the same ratio. So with 12 wheels, I can make 4 tricycles. With 12 pedals, I could make 6 tricycles. So 4 is less than 6, so I can only make 4 tricycles. My wheels are going to be limiting again. My pedals will be left over, and this time I'll have 4 pedals remaining. Okay. Before we get into percent yield, let's start trying to apply this to a problem. So let's go to your notes. Okay, so Here we have a synthesis reaction. Nitrogen is reacting with hydrogen to produce ammonia. First order of business, balance this equation. Hopefully you're thinking, I can put a 3 in front of hydrogen. I can put a 2 in front of ammonia, and that'll make it just 1 in front of nitrogen. Now these numbers, these masses underneath each of the substances, the ones that are not in parentheses, the ones that are the reactants, I'm telling you the mass that we're starting with. So we're going to start this reaction with 16 grams of nitrogen and 6.2 grams of hydrogen. So up first, we've got to try to figure out which reactant is limiting. In order to do that, I need to see, well, with 16 grams of nitrogen, how much ammonia can I produce? And repeat that same sort of calculation for hydrogen. With 6.2 grams of hydrogen, how much ammonia can I produce? So we'll start with nitrogen. Take the number I've been given, rewrite it along with the units. Really recommend being super specific with your units. I'm in grams. I need to get out of grams and into, hopefully you're thinking, the mole. So 1 mole of N2 would have a mass of 14 plus 14 gives me about 28 grams. Okay, so now I've got in terms of moles of N2. I want to figure out how much ammonia can be produced based on my starting amount, my 16.0 grams of N2. I can use the balanced chemical equation. For every 1 mole of N2 that is put in, I can produce 2 moles of NH3. So if I go through and I just cancel, grams of N2 cancel, grams of N2. Moles of N2 cancel with moles of N2. And I'm going to get an answer in terms of moles of NH3. So I'll take 16 times 2, 32. I'll divide that by 28. And I could produce, we'll go 3 sig figs, 1.14 mole of ammonia. Okay, so this calculation basically assumes that nitrogen is the limiting reactant. I don't have anything about hydrogen in here. I'm assuming that nitrogen dictates how much ammonia can be formed. Excuse me. I'm going to repeat that same sort of calculation, making the opposite assumption. Now I'll assume that hydrogen is my limiting reactant and there's plenty of nitrogen to go around, and I'm going to see how much ammonia can be produced from 6.2 grams of hydrogen. Take the number I've been given along with the units, be specific. Got it in grams, I need to get to moles. I know that 1 mole of H2 has a mass of about 2 grams per mole. And based on the balanced chemical equation, for every 3 moles of hydrogen, I can produce 2 moles of NH3. Grams of hydrogen cancel, moles of hydrogen cancel. I'm left again with just moles of NH3. So I'll take 6.2 times 2. I guess I could have just canceled those 2's as well. And I'm coming up with about 2.1, we'll go to the correct number of sig figs, moles NH3. Okay, so which one of my 2 reactants, nitrogen or hydrogen, is limiting? Hopefully you're thinking N2. Why? Well, if you look at the amount of product that can be produced, nitrogen only produces 1.4 moles of ammonia. My starting mass of hydrogen would produce 2.1 moles of ammonia. 1.14 is obviously less than 2.1, so that means nitrogen is going to run out first. You can say nitrogen produces fewer moles of NH3. Therefore, it's limiting. Okay, I have the tendency to kind of combine question 1 and 2 together, but we'll do them separately. What mass of NH3 can be made given the mass of reactants? Well, now that I know that hydrogen is in excess, I can kind of ignore it for any of my calculations about limiting reactants. I know that there's going to be some hydrogen left over at the end, so it does not get incorporated into any of my calculations right now. I know that I should be able to make 1.14 moles of NH3. It's asking for mass. Oh, I can just use the molar mass of ammonia to get that calculated. And 1 mole of ammonia would have a mass of 14 from nitrogen plus 3, 1 from each of the hydrogens, about 17 grams. So 1.14 times 17. If everything goes perfectly, I should be able to make about 9.4 grams of ammonia. Okay. Put a star next to number 3. This is always the trickiest one for new chemists to work with. What mass of excess reactant will remain? So as this reaction has taken place and our nitrogen is getting used up, some hydrogen is going to be left over. I've got enough hydrogen to make 2.1 moles of NH3, but I'm going to stop after I produce 1.14 because then I'm out of nitrogen and there's nothing for hydrogen to react with. So I want to know what mass of my 6.2 grams of hydrogen is going to remain. Okay. There's a couple different ways you can approach this. I'm going to show you one specific way. I'm going to go back to my limiting reactant, nitrogen. And I'm going to kind of go through that same type of calculation that we did up here with ammonia, but I'm going to try to figure out how much hydrogen would be used up. So I'm still going to take nitrogen, and convert it into moles. I know that 28 grams of N2 is equal to a mole of N2. I'm going to use my balanced chemical equation to get from nitrogen to hydrogen. So 3 moles of hydrogen can be consumed every time 1 mole of nitrogen is consumed. And it's asking about mass, so let's get this into grams. 1 mole of H2 would have a mass of 2 grams. All right, grams of nitrogen cancels out. Moles of nitrogen cancels out. Moles of hydrogen cancel out. And my answer should be left in terms of grams. So I've got 16 times 3 times 2. I'm going to divide that by 28. And I come up with, this is really my only measured value, 3.43 grams of hydrogen consumed. Or used, sure. A lot of students make the rookie mistake of being so excited that they have a number that makes sense. It's a mass, it's not too big. Great, I'm done. Careful, it's asking what mass will remain. I know how much I start with, 6.2 grams. I'm going to subtract 3.43 grams, that's what gets consumed. And be careful with sig figs here, this is a subtraction. So you can't go to as many places after the decimal point as you might initially think. I've got 1 place after the decimal point, 2 places after the decimal point. I'm limited to 1. So about 2.8 grams of H2 remains. That's just unreacted hydrogen. Okay, that is the bulk of the math. Obviously, these require a pretty decent amount of work, but if you look, it's the same concepts we were talking about in the previous lesson. We just have to go through that process twice to figure out which of the reactants will run out first and really limit the amount of product that can be produced. The next question asks about percent yield, so let's get back into the notes and finish up that discussion. So percent yield is a calculation you might do if you're a synthetic chemist, if you're trying to make a new molecule in the lab, and you want to kind of evaluate how it went, how effective the reaction was. So it's just really a way for us to evaluate how well did everything go. And it's a pretty simple formula. Percent yield is equal to actual divided by theoretical, and since it's a percentage, times 100. Actual, what did you actually measure when you got into the lab, you rolled up your sleeves and you ran your experiment. And in theory, if every single molecule of reactant was converted to product, how much could you have made? So we'll kind of go into that in a little bit more detail, but definitely get that formula down. It is not on your reference table. So a little bit more about the theoretical yield. The theoretical yield is the maximum amount of product that can be produced from a given amount of reactant. This is a calculated value. This is what you're calculating every time you do a limiting reactant problem. How much could I make if everything went perfectly? Actual yield. I went into the lab, I ran the experiment. How much did I actually collect? So the measured amount of a product obtained from a reaction. And it is measured. There's really no way to get the actual yield without running the reaction. Not every time you run a reaction do things go perfectly. People like to try to draw parallels between chemistry and cooking. If you're baking chocolate chip cookies and you take a dozen little chocolate chip cookie dough balls and you put them on the cookie tray, you put them in the oven for 10 minutes or whatever, and you pull them out, you know you're going to get 12 cookies. If you put those same 12 raw cookie dough balls in a chemistry oven, air quotes included, when you pull them out, you're not guaranteed to get 12 cookies. You might get, 7 cookies, 3 of them didn't cook, and 2 of them turned into baseballs. It is not as easy to predict. A lot of the reactions we look at are very simple, and there's really only like one product that can be formed. But as you make your way up the ranks in chemistry and you start looking at larger, more complicated molecules, it's not uncommon to have your products producing something other than what you wanted, like other side reactions that you weren't anticipating and you didn't want, or simply for a reaction to just not occur to the fullest extent. Oops. So let's go back to the notes and wrap up that problem. So our last problem to wrap up this example, we're going to show our formula. Percent yield is equal to actual divided by theoretical times 100. Okay, so where do these numbers come from? The way I've set up the practice problems and this example is the number in parentheses underneath the product. That is your your actual yield. When you went into the lab and you ran that reaction, in this case, you collected 10.1 grams of NH3. Your theoretical yield is what you're calculating. Let's put it in a different color so maybe it'll stand out a little bit more. You calculated that if 16 grams of nitrogen reacted completely with hydrogen and everything went perfectly, every last molecule of N2 was successfully converted into NH3, you would make 19.4 grams of ammonia. So that is your theoretical yield. In theory, if everything goes perfectly, how much could I make? Now it's hopefully a very straightforward math problem. 10.1 divided by 19.4 times 100. Be careful with your sig figs. I'm getting about 52.1%. Not a spectacular yield, but that happens. And it doesn't work out perfectly in the lab for you every time you go in there. All right. These types of problems are challenging. These are the 4 questions I will ask you about limiting reactant. Identify which is the limiting. That's probably the most time-consuming step as you go through calculations for both reactants. You can often combine 1 and 2. If I just kind of tacked on, we'll circle it in green, this conversion, and I put it at the end of each of those, I could calculate grams and kind of skip over this. Number 3, the calculating mass remaining. That's always the most complicated one for students. Don't forget, you're generally calculating how much H2 or how much reactant you used. Don't forget to subtract. And the percent yield is pretty straightforward, but be careful. The number of times I see students try to plug in basically the percent error formula. They'll do like actual minus theoretical divided by theoretical. No. It's what did you make in the lab divided by what could have you made if everything went perfectly times 100. Practice with these chemists. This is a challenging concept. All right, that does it for today. Thank you for tuning in, and I hope you found this helpful.